maxima, minima points of inflection. And I think the best way to do this is simply start and begin with the examples immediately. Just a reminder, though, that the notes on the theory and the concepts are on the Moodle site, and you need to go through those. So in this case, we want to determine the critical points of the graph. And when we find the critical points, we mean the maxima, minimum points of inflection. And you'll find in many textbooks, they will say possible points of inflection or possible maxima. And in this example, you will realize why that is so. So let's have a look at this. F of x is equal to arctan of x minus x plus 1. Now, I just want to highlight how important it is that you know your previous mathematics. Yeah, we are merging, we are integrating critical points and inverse trig, inverse hyperbolic. You would have found out in many of the examples that you have attempted in the tutorials and the exercise for the major test 1, that your past mathematics, things like trigonometry, complex numbers can appear anywhere. Now let's go immediately to the solutions. Determine the critical points. If I want to find maxima and minima, I need to find the first derivative. So I'm finding the first derivative, and once again, emphasis is on differentiation, the differentiation process. In this case, it's a straightforward differentiation. It could be a logarithmic differentiation, implicit differentiation, it could be any differentiation technique applied for maxima and minima. Okay, the derivative of arctan is 1 over 1 plus x squared. Derivative of minus x is minus 1. The derivative of 1, that's equal to 0. And what I'm going to do immediately is find our second derivative. They asked us for the critical points, which includes possible points of inflection. Now, in order for me to do the second derivative, I could use the quotient rule. But in this case, I'm not going to use that. And the reason is very simple. Look at the fraction. The numerator has a constant, and that constant is 1. The denominator has that function, which means I could use my knowledge of exponents and take that entire term, raise that to the power minus 1. Of course, subtract 1. Now that allows me to find the second derivative a lot quicker and a lot easier. So multiplying using the chain rule, it will be minus 1 around 1 plus x squared. Do we stop there? Not at all. Times the derivative inside of that argument times 2x. And of course, the derivative of minus 1 is equal to 0. Simplifying, I get minus 2x. And of course, minus 2 is the index. Divide that by, open brackets, 1 plus x squared all squared. Now we have both our and the second derivative. The theory states if I want to calculate either maxima or minima, I must take my first derivative and put that equal to 0. That you know from basic school mathematics. So my first derivative is 1 over 1 plus x squared minus 1. Put that equal to 0. Transpose the minus 1. 1 over 1 plus x squared. is equal to 1, multiply through by the LCD, 1 is equal to 1 plus x squared, transpose, and that gives me x equal to 0. Now, of course, that x is equal to 0 could be any value. In this case, it happens to be 0. 10 minus a quarter, 0.25, anything. Now we have to question ourselves. Well, okay, if x is equal to 0, is it a maxima? Is it a maximum or is it a minimum? And this is when our second derivative test comes in. And this is a test that establishes whether that value that you have calculated, in this case, x equal to 0, is it a maximum value or is it a minimum value? And how do we do that? We substitute that x value into the second derivative. Now, my second derivative is negative 2x over 1 plus x squared, all squared. Substituting x equal to 0, I get negative 2 times 0, 1 plus 0 squared. And that's all squared, 0 over 1, and that gives me 0. So what does that make? X equal to 0, a maxima, minima? Well, this is where we need to know our theory. And the theory states if the second derivative at a particular point is greater than 0, then it's a minimum. On the other hand, if the second derivative is less than 0, then it's a maximum. But in this case, we get exactly equal to 0, neither positive nor negative. So what's our deduction? What is our conclusion? We cannot establish whether it's maxima or minima, meaning that x equal to 0 is not a maximum or minimum. Therefore, there is no max or minimum value. So x equal to 0 is not a maximum, neither is it a minimum value. Well, we got the first part out of the way. To find maximum, minima, first derivative equal to 0. What about points of inflection? Well, for points of inflection, we need the second derivative to be equal to 0. And if the third derivative, that point, is not equal to 0, then it is a point of inflection. So let's take our second derivative, which is negative 2x, so our second derivative from our previous slide. Let's just go. There's our second derivative. Minus 2x over 1 plus x squared, all squared equal to 0. Let's work that out. Multiply by 0, 1 plus x squared. That gives me minus 2x equal to 0. And therefore, divide that. X equal to 0 is a possible point of inflection. And once again, I want to emphasize it's a possible point of inflection. So how do we establish whether it is a point of inflection per se? We'll have to look at the third derivative. Now, let's find the third derivative. We know what the second derivative is. He has it here. That means I'm going to use my quotient rule. So yeah, I'm going to use my quotient rule. Why will I use the quotient rule in this case? Because the numerator has variables. It's not a constant, as in the first derivative. So I'm going to take the denominator and square all that. Then I'm going to put that down. 1 plus x squared all squared, multiply by the derivative of the numerator, subtract. Now I leave the numerator and multiply by the derivative of the denominator, which will be 2 times 1 plus x squared multiplied by 2x. Oh, that is pretty lengthy, isn't it so? But we don't need to simplify because we only want to establish whether the third derivative at x equal to 0 is going to be any value except 0. So taking our third derivative at 0, every x value over there, just put in 0. So that will become 0, that's all squared. 1 times minus 2, that gives me minus 2. This entire fraction here, that entire term has a 0 there and a 0 here. 0 times 0, that will simply give me 0. In the denominator, notice that is 0. So I'll get 1 all squared, that will give me 1. Meaning I get an answer of minus 2 for the third derivative at 0, and that minus 2 is not equal to 0. Therefore, my deduction is that the value where the second derivative is equal to 0, which is 0 in this case, is a point of inflection. So in this example, I try to show you the theory and the concepts related not only to finding the maxima and minima, but also the corresponding tests that we have to do. In the first case, to establish whether it's a maximum or minimum, in our case, we find that there's no maxima or minimum. And in the second example, to find the points of inflection, we use the third derivative test. And if that third derivative at a particular point gives me an answer which is not 0, then it is a point of inflection. Okay, I think we can go through the next one. Next example. Consider the curve y is equal to e to the minus x sine x. Show that the possible points of inflection occur at x equal to pi over 2 plus k times pi. Let's get right into it. We got y is equal to e to the minus x sine of x, and we want points of inflection. And for points of inflection, we need the second derivative. Our first derivative, e to the minus x times sine of x. One function multiplied by another, product rule. So yeah, I'm going to use my product rule. Let's differentiate the first, e to the minus x times minus, leave sine of x, plus, now I leave e to the minus x, times the derivative of e to the x, which is cos of x. So I get negative e to the minus x sine of x plus e to the minus x cos of x. Now I need to find my second derivative. I want you to look at that function very carefully now. Because if you look at it, those are two terms. The first term is the product rule, minus e to the minus x sine x. The second term is also a product rule. So I have to use the product rule twice. But this is when your manipulation, your algebraic manipulation of terms plays such a major role to reduce your working out. There's a common factor there. We can remove the common factor of e to the minus x. Then I'm left with cos x. It should be the other way around, but I just want the first term to be positive and minus sine of x. Now that will make finding the second derivative a lot easier, because now I can use the product rule again, but then that becomes my f and that bracket becomes my g. So working that out using the product rule, let me find the derivative of e to the minus x first. That's minus e to the minus x. Differentiate the first one, leave the second one, plus now you leave the first and you differentiate. What's the derivative of cos? Minus sine. What's the derivative of sine? Cos x. And I'm going to remove e to the minus x as a common factor. Be careful, I've removed e to the minus x and there's still a minus over here. So that minus must go into that brackets there. So that will become a negative cos x plus sine x. And I've removed e to the minus x. I'm left with minus sine of x minus cos of x. The signs cancel. I get e to the minus x multiplied by minus 2 cos of x. So there's my second derivative. And I know for points of inflection, the second derivative must be equal to 0. Therefore, e to the minus x times minus 2 cos of x is equal to 0. E to the minus x is equal to 0, or minus 2 cos of x is equal to 0. And that tells me that cos of x is equal to 0 dividing by the minus 2. Now, before I do cos of x, let's have a look at this. We can introduce ln on both sides, and we will obtain minus x is equal to ln of 0. Now run to your calculator. What do you obtain? That cannot be found. So there's no solution in that case. So let's go to cos x. If cos x equal to 0, or cos of 0. Do you recall the cos graph? Where does that start? At 1, 0. What's that value? That is 90 pi over 2. However, we want the general solution. And with the general solution, where cos x equal to 0 is pi over 2 plus k times pi. That's a special case because it occurs again at another pi over 2. So you add in all the time the value pi over 2, which is 90 degrees. And there is your answer. And you have shown that the possible point of inflection occurs. And notice they ask for possible points of inflection. So you don't have to do the third derivative. This is a possible point of inflection. We're not going to check whether it is exact a point of inflection by doing the third derivative. Next example. Example 3. The signaling range x is proportional to r squared ln 1 of r. Find r for maximum range. Let's just go immediately to the solution. X is proportional to r squared ln 1 over r. Do you recall from physics what you have to do? If anything is proportional, then you can make that an equation by introducing a constant. I'm going to introduce k, so k is my constant. R squared, Now, look what I'm going to do. To make things a lot easier, ln r to the minus 1. So I get x is equal to negative kr squared ln of r. Do you recall? That's right, your log rules. And once again, in these examples, notice how integrated all the different sections that you've covered before and that you know even from school that you should be familiar with. The ln of t to the power r is equal to r ln of t. Of course, I should put it in here, but this is just multiplication, so I can put it in the front. Why would I do that? Because now my derivative is a lot easier to calculate. So if we want maximum, so it's for maximum range, we want the derivative with respect to r to be equal to 0. So let's look at our derivative. There's r and there's ln r. So it's r times r, which means we're going to use the product rule. So I'm going to bracket off that part and that part for the f and the g. Therefore, my derivative, let's work out, minus kr squared. The derivative of r squared is 2r, so that will become minus 2kr. Then you leave ln of r plus, now you leave the first bracket and you find the derivative of the second. Ln of r is 1 over r, and that must be equal to 0. Can we simplify? Let's simplify. Minus 2kr ln of r minus kr equal to 0. I'm going to take the k and the r out as a common factor. I get negative 2 ln r minus 1 equal to 0. Therefore, kr is equal to 0. First bracket equal to 0, or my second bracket is equal to 0. Transpose, I get ln r 1 divided by 2, and r is equal to the ln r is equal to minus a half. Therefore, r is equal to e. Oh, okay, I made that a little bit too big. This will be e to the power negative a half. Use your calculator and you'll obtain 0.606. What about this case? R equal to 0, which doesn't make much sense at all. So obviously that will not be applicable, meaning we have our value for maximum possible maximum range when R is equal to 0.606. That's the end of this lecture.